Turtles are ancient creatures that have been on the earth for hundreds of millions of years. For a group with such an unusual adaptation, one that comes with some pretty heavy baggage attached, they have been able to diversify and adapt to a surprising range of habitats, from deep oceans and vast rivers, to lakes and small streams, to land, where they thrive in forests, mountains and baking hot deserts. Perhaps striking out into unfamiliar territory is easier when you have your own personal force field. Today there are over 300 living species of turtle, which form the order Testudines. Each one sports a shell, their trademark feature, which mainly serves as the ultimate defence, but has other uses too, like environmental protection and the storage of fat, minerals and water, a bit like a camel's hump. It's easy to think of the shell as something these creatures carry around and tuck themselves inside when something large and hungry appears. But the turtle doesn't carry the shell on its back, the shell is the turtle's back, created from its skeletal system and incorporating the spine and ribs. This means you could not pull a turtle out of its shell, not without a great deal of force anyway. It would be like trying to pull a person off their legs. The turtle's shell is formed of two parts. First, the dome-like carapace above, made from about 50 interlocking fused together bones, and capped with scutes made of keratin. This joins with the flat plastron beneath, made of only 9 bones, during the turtle's embryonic development. Together, these structures completely encase the animal, protecting all its squishy bits from harm. The shell is obviously a useful bit of kit, and no other vertebrate has anything quite like it. So how did turtles get them? What evolutionary path did they take to arrive where they are now? Well, it's a bit of a tricky one, and only in the last few decades have we gotten anywhere close to unravelling the mystery. For a century after its discovery in 1890s Germany, the oldest turtle ancestor known to science was the late Triassic Proganachelles, which had a complete shell. This was a land-dwelling animal, so it seemed sensible to assume that turtles evolved shells on land, and then took to the oceans. But we lacked evidence to show how the shell actually got its start. This lack of partial shells made some scientists think the structure must have arisen surprisingly rapidly, perhaps too quickly to be captured by the fossil record. But others weren't convinced. Another issue in unpicking turtle evolution comes down to their unusual skulls. Temporal fenestrae is the scientific name for holes in the skull behind the eye sockets, and the majority of vertebrates have them. You may have spotted them on dinosaurs, who we're more used to seeing without their skin on. They provide space for jaw muscles to expand, allowing for a stronger bite. There are 3 clades of reptile that are identified by these temporal fenestrae. You have synapsids, with 1 skull hole, which evolved into all the mammals. You have diapsids, with 2 holes, which gave rise to dinosaurs and all modern reptiles and birds. And you have anapsids, with no holes, older ancestors of reptiles who are now all extinct. Or are they? Turtle skulls are solid lumps of bone with no temporal fenestrae, which would seem to make them the only living anapsids. If this were true, it would make turtles the sole survivors of an ancient clade which the main diapsid reptile branch split away from in the early Permian period, close to 300 million years ago. But in the last 20 years, new fossils have been discovered that have revolutionised our understanding of turtles. For starters, we finally found some heroes with a half shell that show how the structure may have got its start. And we also found older turtle fossils with small or closing up temporal fenestrae, which revealed that turtles actually were most likely diapsids all along. They just mischievously ditched the key characteristic that scientists were using to identify that group. DNA evidence now places turtles here, close to the archosaurs, which include crocodiles and modern birds. Though not everyone agrees, for now that's the closest science has come to a consensus. But to actually understand how the turtle body plan came about, we have to go back in time. 260 million years ago, living life on the edge, dangerously close to the Permian mass extinction, the oldest known turtle ancestor, Oenotosaurus, goes about its business. This 30 centimeter long animal looked like a surprisingly circular lizard, and quite unlike a turtle. But peel back the flesh and its bones reveal a secret. Like the turtles of today, Oenotosaurus had a short spine, with only 9 vertebrae. But the truly unusual part of this species was its ribs. Ribs are a part of the skeletal structure that tends to vary very little from creature to creature. Some have more, some have fewer, but generally, one rib cage is much like another when it comes to function and form. That's not the case for Unitosaurus. This animal had very broad ribs, which actually overlap slightly. This would have had the effect of stiffening its trunk. Most vertebrates have ribs that can flex as they breathe, but not turtles, whose highly modified ribs form the shell, and, at least to an extent, not Unitosaurus either. Not only did it have these strange chunky ribs, Unitosaurus, like modern turtles, also lacked the intercostal muscles, which move the ribcage up as our lungs expand. For most animals, breathing is quite a useful skill, and so turtles have a workaround, a specialised muscle sling system that wraps around and squeezes the lungs. And it seems Unitosaurus had a rudimentary form of this too. It's interesting to consider how all this weirdness could have come about. In most vertebrates, both the ribs and abdominal muscles perform the joint function of stabilising the body, preventing torsion while an animal moves, and also assisting with breathing. In turtle ancestors, the ribs began to do more of the former, while the abdominal muscles did more of the latter, until eventually the two structures stopped working in unison. The abdominal muscles helped the lungs, while the ribs provided stability. No longer required to do two jobs at once, the two structures would quickly, at least in evolutionary terms, start to specialise. But how would all this aid survival? What evolutionary edge did a stiffer torso offer that it was worth these remarkable ribs, which gave zero protection and not only affected Unitosaurus's breathing, but also its ability to move? Unitosaurus would have been unable to bend its torso to increase its gait as it walked, the way crocodiles and lizards do today, making it rather sluggish. Well, it's thought that Unitosaurus was a burrowing animal, which spent at least part of its time underground. A stiff, strong torso with reinforced ribs would allow the animal to withstand the powerful forces it generated while digging. The creature had other traits associated with a burrowing or fossorial lifestyle too, thick forelimbs and large claws. Burrowing may have been a useful practice during the Permian period, which was marked by a more extreme climate than the tropical Carboniferous. It may even have helped to see Unitosaurus or its relatives through the mass extinction event to come. At this point, Unitosaurus's thick ribs helped with digging, and provided the first evolutionary steps which would allow later stem turtles to grow a protective shell. But the proto-turtles wouldn't just be burrowing for long. Living 240 million years ago, in the early Triassic, Papacheles had similar ribs to Unitosaurus, only shorter and straighter. It might have had a sort of internal shell, providing some degree of protection, as the ribs extended upwards into the dermis. Papacheles also had larger gastralia. These are sort of underribs found in many prehistoric tetrapods, including dinosaurs. Unitosaurus had them too, but in Papacheles they reach out finger-like, creating the beginnings of a rigid basket that would in later relatives become the shell's plastron. This may have been to provide an even more rigid trunk for even better burrowing, but some scientists think it would have also helped with swimming. Papacheles' remains were found in Germany, in a fossil bed that was once a shallow freshwater lake. This is far from definitive proof that Papacheles was aquatic, however, and other scientists note that apart from its dense bones, the animal had few adaptations suited to swimming. A Papacheles fossil was found with the bones of some tiny, land-dwelling lizards in its belly, and most of the skeletons that have been uncovered showed signs of predation, so it's perfectly possible the animals were in a lake because another aquatic predator snatched them up. Papacheles may have dug burrows and lived a lightly amphibious lifestyle, slurping up worms, insects and whatever else it could find on the banks of rivers and lakes, its dense bones helping it to swim, if awkwardly, when necessary. Scientists are not in agreement about which turtle ancestors lived in water full-time, which were purely land-based, and which were sort of half and half. Just like modern testudines, there were ancestral turtles across the whole spectrum. But traits which made this animal group excellent diggers, like strong forelimbs, would also have eased the transition to swimming. If you think about it, the motions required are not so very different. Whether swimming or digging, you're using your front limbs to displace material and propel yourself forwards. Moving to the mid-Triassic, a creature called Eorhynchocheles is the first time another notable turtle trait appears in the fossil record, a toothless beak. Eorhynchocheles lived about 228 million years ago in the shallow seas of what is now southern China. Compared to the stem turtles we've looked at so far, Eorhynchocheles was a titan at around 6 feet in length, rivaling the biggest turtles alive today, although proportionally its triangle-shaped head was very teeny. While Eorhynchocheles actually did have small teeth at the back of its mouth, the front formed a keratinous beak. Rather than just grabbing food for tearing like most reptile teeth, which aren't specialised the way mammal teeth are, beaks are useful tools for snipping or crushing, and may have helped the animal access new food sources. But interestingly, many turtle ancestors that lived after Eorhynchocheles don't have a beak. It certainly doesn't seem like the adaptation took off here. This suggests that beaks were a feature that developed multiple times throughout turtle evolution, just one of countless examples that demonstrate how this process is always a more winding road than you expect. One of those beakless ancestors is Odontocheles, which lived just a short 8 million years later and was found in marine deposits in the same part of China. When it was discovered in 2008, Odontocheles was a hugely exciting find, as this is the first proto-turtle with what can firmly be called a partial shell. Specifically, this animal had the bottom half of a shell but not the top, a plastrum but no carapace. It's a valuable clue, which seems to suggest the shell made its big debut underwater. It would make sense for the underside of the shell to develop in water, since you're more likely to be attached from underneath in a 3D aquatic environment than you are on land. As well as protection, the plastrum may have had a role in swimming, keeping the reptile balanced in the water like the ballast and keel of a boat. Odontocheles is the earliest stem turtle with a partial shell that we found, but that doesn't mean it was the earliest that ever lived. Notably, it came only 10 million years before our old friend Proganocheles was walking around with a fully encased bone bubble. Proganocheles is the most famous stem turtle. Discovered in the 1800s, it's been found all over the world. While in the past some saw it as possibly semi-aquatic, like other turtles, it's now thought to be a land dweller that lived quite like a modern-day tortoise, though there are some key differences. For one, Proganocheles had a tail club for defence like an ankylosaur, but a lot smaller, a tack hammer to the Ankylosaurus's mace. It also had a ring of spines around its head, providing some protection for this area, which up to now had remained vulnerable. With the other vital organs locked up in the shell, the turtle's head had become the biggest chink in its armour. After the Triassic, turtles came up with a new technology to stop them from risking their necks, tucking their heads into their shells. This does make all previous stem turtles sound like idiots, but it wasn't a matter of behaviour. The manoeuvre just wasn't physically possible without painstaking changes to the neck vertebrae and muscles, which gradually turned turtles into proper contortionists. The turtle lineage splits into two here, as two methods of neck tucking were developed. The pleurodires tucked their necks in sideways, while the cryptodires retracted their necks directly backwards. These are the two suborders of turtle that exist to this day, and they're also separated by a number of other differences, such as pleurodire having pelvises that are fused to their shells. As you may have realised, the fact we're talking about different groups of turtles that are alive right now means we've passed the most recent common ancestor of all living turtles, which roughly coincides with this divergence between Cryptodira and Pleurodira in the late Jurassic. That means we can now safely refer to everything beyond this point as not a stem turtle, but a true example of glorious turtle kind. Today the cryptos far outnumber the pleuros in diversity and in sheer numbers. There are 246 species of hidden neck turtle to the side neck turtle's measly 79, and all the pleurodires alive today live in the southern hemisphere in freshwater habitats. But it was actually the side neck turtles that developed first, and the cryptodires who then split off from them. The pleurodire method of neck protection was a logical progression from a hypothetical partial neck tuck that much older turtles, including Proganocheles, may have been able to pull off. As for the cryptodire method of pulling the head directly back, the Jurassic animal Platycheles auburndorferi provides an interesting argument for how it may have come about. While this was an early pleurodeer, Platycheles could also partially retract its neck into its shell like a cryptodeer. Just like the famous alligator snapping turtle of the modern age, it was an ambush predator, who would lie in wait at the bottom of shallow waters, then strike with surprising speed. The case study of Platycheles demonstrates how cryptodeer neck retraction may have evolved, not initially for protection, which would at first have been rather limited, but to aid the head thrusting forward quickly to capture prey. Now that we're onto real turtles, there are many more potential directions we could go. Dozens of possible pathways to trace towards the 14 families that exist right now. We could look at the soft-shell turtles, who in the late Cretaceous decided to throw away all that hard work developing the animal equivalent of plate armour for an extra turn of speed. We could examine extinct giants like Archelon, which grew to the size of small trucks. Look at the highly specialised adaptations of sea turtles that could hold their breath for 7 hours, or consider tortoises and just how and when they made it back onto land. But those journeys will have to wait for another time. For now, we've succeeded in our initial mission. We've journeyed all the way from the earliest known stem turtle to the beginnings of the modern turtle family tree, and seen the shell grow from strange misshapen ribs to a fully protective casing that the animal could tuck itself away inside. There are still plenty of mysteries to overcome about turtle evolution, but just like the animal itself, we are making slow and steady progress.